Hi, so welcome back. So we did talk about boundary layer displacement thickness, right? What I'll do, so there's something else to be done next, right? Which is say boundary layer momentum thickness. Okay, let me write that down. We denote it by the variable theta, right? So boundary layer momentum thickness, which we denote by this theta. All right. So again, we will try and understand what that means. Okay, and we will do the math to understand that. Now, before we do that, now let us sort of look at a problem that what sort of questions could be asked, right? What sort of answers are we looking for when we are looking at, a boundary layer momentum thickness or displacement thickness and then so on and so forth, right? So, so for example, so this is a problem we could have. A sharp flat plate, a sharp flat plate, right, with dimensions L is equal to 1 meters, B is equal to, so length 1 meters and breadth 3 meters, is immersed parallel, okay, to a stream of velocity, to a stream of velocity 2 meters per second. Okay. The question is, so you have a physical problem like this, right? So you have a flat plate which has certain dimensions and you just immerse it and there is a flow which is happening across it. Okay. So now what should you be concerned about? So what you should be concerned about, or the questions that you could have is find the drag, okay, on one side of the plate so find the drag on one side of the plate, okay, and at the trailing edge, which is the far end of the plate, okay, at the trailing edge, right, find delta star and theta. So, what exactly is this theta now? Okay, right, for there are some cases given to you. Okay. Now, A, so case A is when it is for air, okay, when rho is 1.23 kg per meter cube, nu is 1.46 into 10 to the power minus 5 meter square per second, right. B is water, rho is 1000 kg per meter cube and nu is 1.02 into 10 to the power minus 6 meter square per second. This is very interesting. Okay? So, hopefully we will get some very good insights into this once we do this. So, to answer this question, we should be able to find out delta and delta star by now, right? But we do not know what this theta is, and which is the momentum thickness, right, which is boundary layer momentum thickness, and we also do not know how to find the drag, right. So, that is also something we need to find out. So, let us see how we will go about this problem. Now, what exactly is this momentum thickness? Okay. Now, and how do we sort of go about this? Now, so what we did in order to calculate the boundary layer displacement thickness, right. So, we took the mass flow, right. We basically exercised the fundamental equation of conservation of mass, right. So, if I were to go back, okay, to this picture that we had drawn last time, okay. So, this is a picture which we had drawn, if you look at this. So, basically what we said is that whatever mass enters, at section 1, right, will need to leave section 2, because that is the fundamental law of conservation of mass, right. Mass cannot be created or destroyed. Now, having said that, so when it enters, right, the space, it is entering at a distance h naught, but for that entire mass to exit, it cannot exit only through h naught, it needs more distance, more height, it needs more space, so to speak, because in the scenario of existence of the boundary layer, it displaces or pushes the external flow away from itself, right. So, this is actually acting like almost a solid obstruction, right, solid obstruction, and so it pushes away the flow. And so, therefore, you can see the streamline, it get displaced, okay, it is displaced, and therefore, you need a height which is h naught plus delta star to allow that entire mass, incoming mass, to exit, right. So, that is what we did. Now, of course, in this particular case, you have a mass which is coming in with velocity, right, and we have a mass which is going out with a velocity, So, clearly, there is also, a change in momentum when that happens, right, because you can see that the velocity is changing, the velocity is not same, right. Now, so what does that mean, right? What does that mean in terms of physically, what does that mean? So, there, when I do that, right, what kind of what does that boil down to, right? That I need a height of the height of delta star, okay, over and above my h naught for my mass conservation to be valid. Then what sort of a height should we need for my momentum conservation to be valid, because momentum also needs to be conserved, right. So, it is basically the same principle again, it is basically the same principle again, okay, that we are going to exercise the or implement, right, the law, the fundamental law of conservation of momentum. So, if I do that, okay, again, so I am not going to sort of repeat the diagram which we did. So, if you look at this picture here, if you look at this picture here, so we are looking at this height h naught, right, which is extending outside of the edge of the boundary layer. So, if I do that and I have a small little element of dy, so if I do that, let us go to the next page. Okay. So, A is essentially this is, yeah, okay, momentum flux, is that right? Yeah, momentum flux, okay, momentum flux across dy, okay. Dy is a small distance, so what the heck. Let me just draw the little picture here for reference. So, this is the plate, okay. This is y, and we do have that. So, what we are going to do is we are going to consider some height, which is this height is say h naught, right, and what we are doing is considering a small element, and this is dy, right. So, here y is 0 and here y is h naught, right. So, what we are saying is momentum flux across this little dy is nothing but u into dm, because here the velocity, it has a velocity profile uy essentially. So, it is So, when I say u dm, basically I mean u y dm. So, that is why, so we will have to integrate it. Okay. So, u dm, right, u dm. So, now then we are going to use some math, okay, u. So, what is the mass? What is the mass of this dy, right? So, density and velocity which goes through that dy, right. So, this is essentially the mass flux. So, then what this becomes is rho u square dy, right. So, this is what actually goes through. So, this is what actually goes through, right. Now, B is the hypothetical momentum flux, okay, across dy. Okay. So, hypothetical momentum flux across dy basically means this is equal to, because again for inviscid case the velocity profile will be u infinity. So, into dy, right. Okay. So, oh sorry, not across dy, it should be into dm, right. So, is nothing but dm, right. Now, this total mass, so this mass, so then this is essentially this, therefore, this, now this dm remains the same, right. Now, what we are basically saying, this you have to be a little careful when you do this. So, u infinity dm is still this, right. Does it make sense? Okay. So, then this is essentially rho u infinity dy, right. So, this is essentially due to the this is the momentum flux due to free stream. Okay. Now, what you are basically saying is we have a little mass, okay. We have a little mass, that mass is not changing, and we are saying that this mass here, right. So, this mass here is rho u dy, right, rho u dy. This small u is basically in the presence of the boundary layer, the velocity is u, right, u y. So, u y dy. So, this is the mass corresponding to the velocity u and height dy, right, per unit length. So, now for unit depth. So, now the thing is the momentum flux, so what would be the momentum, right, with which this small mass will be actually moved? How will it be moved? In the sense that when the flow comes in, right, it is going to move this mass, right. How will it move it? It will move it with velocity u. So, therefore, what is the momentum? Corresponding momentum. So, it is u into dm. So, u into this. However, the same mass, right, if it is existing here, but if what came in, right, what came in was not this small u, was the hypothetical velocity, which is u infinity. Then what the momentum would be? Momentum would be this u infinity, right. So, u infinity is essentially the momentum, which is the basically for the inviscid case. So, again the so the obviously b is greater than a. So, the loss or the decrement in the momentum, right, is b minus a, which is equal to rho u, okay, u infinity minus u dy, okay. And if we integrate that, the total decrement, so that we shall integrate from 0 to h naught, right, 0 to h naught. That would be my total decrement in the momentum, right. Now, so what we did like last time, in terms of the mass, we said that this is the total decrement in the mass, right. So, the mass needs a separate height to move, right. It cannot, the entire mass cannot exit through height h naught. It needs an extra height, which was delta star. In this case, you need an extra height for this momentum to exit, right. So, let that height be theta, right. So, let that height be theta, so that then, right. So, when I do that, so then I call this, how do I therefore equate it, right. So, then I say rho u infinity square, which is theta, right. Rho u, so this is the total momentum flux, right, through that extra theta. So, what basically I am saying is that you've got this delta, this plate, right, and you've got this say boundary layer, right, and you've got this boundary layer, right, and this height is delta, right, and this height is h naught, right. Then I need another height, which is like this bit, and that is theta, right. So, now I can say that when I have, so in this case the way to look at this, right. So, the way to look at this, that if, right, so if I have a so if I have this flow which is entering here, right. So, the way to look at this, what I am trying to say is that if the flow enters here at this location, right, at the height h naught, it has a certain momentum, right. Now, for that entire momentum to be conserved, so that now I need to see the entire momentum go out at the exit as well. Now, that is not going to be possible with just the height h naught. One would need an extra height, and that extra height, corresponding height, is theta, right, theta. So, which is similar to what we were saying about the displacement thickness as well. So, then in this, so rho infinity square this. So, if this one I can also write this, this I can write as u infinity rho u infinity theta, right. So, basically what I'm saying is that this entire decrement in the momentum flux, right, is equal to what? Now, if you look at this, this is essentially the mass which is corresponding to this height theta, right. So, what you mean is that the mass, what is the momentum generated by the mass corresponding to height theta, right. So, in other words, what you can say is that what does the boundary layer momentum thickness. So, we said boundary layer momentum thickness. So, that essentially would mean the momentum, right, caused by the free stream across a mass, right, which has a height theta, right, and this theta is, so therefore, this is the height, right. So, this is the momentum which is caused, right, this momentum is caused due to the free stream over a mass corresponding to the boundary layer momentum thickness, and this, right, is equal, this and this entire momentum is equal to the momentum decrement from section 1 to section 2, right, and this whatever height h naught you take. Now, h naught could be anywhere, it could be delta as well. Okay. So, that is what, so this basically, so that, so all, or another way of looking at it is that delta is the height of the fluid, right, the mass, so the height of the fluid, so the mass of which, right, corresponds to the momentum caused by the free stream, right, which accounts for the momentum decrement as the fluid moves from section 1 to section 2 over a boundary layer. Right. So, that is essentially our momentum thickness. Okay. So, well, having said that, so now again we have all this equation here. So, if I were to equate this, right. So, this is our equation that we have, this is our equation. So, if I were to equate this, what I would get is this 0 to h naught u by u infinity 1 minus u by u infinity. Again, what you increasingly see here is that if you can find an expression, so if you can find an expression for the velocity profile, for this, then you should be able to find out expressions for displacement thickness, momentum thickness, and so on and so forth, right. Okay, so now having come across that, okay, now let us sort of go ahead and okay, so we should be able to get some, let us see how we are going to do this. Now, okay, so there are a few things how to go about this solving the problem. Of course, you can insert the values of u and so on and so forth and do that. Now, one of the important things, one of the reasons of studying the boundary layer is because of this whole drag thing, right. It is a viscous effect. So, so this question here, find the drag on one side of the plate, that is important, right, that is a very important thing. So, so we found out various expressions and all that. So, now let us just go ahead and see some formula, and we will kind of develop that and then do this problem, right, before going into the details of it. Some details as to how Prandtl came upon his formula, and Blasius was able to give, who was Prandtl's student, by the way, in 1908, he was able to propose solutions for this. Now, these are things that we will discuss as we go further in the course. So, as of now, what we know, right, let us just look at some formulas, right. This is basically coming from Prandtl's boundary layer theory. Now, this is something that we know. Okay, let us go further down. Okay. So, what we know so far is delta by x, right, which is 5.5. So, I am going to just write that, right. This is one of the things that I know. Now, now CF is coefficient of friction, actually, right. Now, this is given as this. Let us see. Okay. These are things we tend to use, right, in our study, right, and this is an expression that this is for displacement thickness, right. So, that is, I think we wrote something about 1.83, right. So, similar. Okay. Now, wall shear stress, okay. This is wall shear stress, which also depends on x, of course. Now, this is an expression for wall shear stress. So, you know what wall shear stress is, right. So, shear stress is nothing but, I think we talked about this in detail in the first couple of modules. Okay. So, sort of remind yourselves about that. So, these are some formulas which we are kind of trying to do. Okay. 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 So, now this is an expression for wall shear stress. Now, essentially this should be sufficient, because when we are talking about drag, right, what we get from the boundary layer is essentially an expression or understanding of the shear stress, right. We talked about the shear stress right at the beginning. So, shear stress, so you can see du dy, so which is how is the velocity varying as we move along y, and this is obviously the maximum near the wall, right. So, because it is 0 near the wall, just above it it's a little more, and so on. That is how we get the velocity profile. So, therefore, the shear stress at the wall is maximum, obviously, right, and so as we go it decreases. So, now, so therefore, this is the shear stress. So, this is the shear which is being caused by the fluid on the surface, right, on a solid surface. So, therefore, it causes a drag. So, all we are going to talk about the drag is integrate this shear force, right. Shear force, it's a shear stress, right. So, we are going to integrate it over the area, and that should give us the drag, right. So, if I were to calculate the drag, which again will depend on the length, right, the x that I am considering, right, because as you can see here, if you see here, the shear stress, the wall shear stress, right, is inversely proportional to the root of x, so there is no like linear correlation. Okay. So, dx, so if you see this, okay, so we are looking at length x, right, tau w, okay, x dx, right, and you multiply that by the breadth of the plate, right. So, dx is basically b tau x dx, right. So, if I use the above formula, what I get is this 664 b under root rho nu u infinity 1.5 under root x. Okay. So, you can cross check if I did that right. Okay. So, what I did is I integrated this tau x into dx, and I multiplied that by b, right. What I got here is 0.664 b, right, the b comes here, under root rho nu, okay, this u infinity that, and yeah, okay, right. So, this is what we get x. So, this is, so cross check if this is okay, right. So, this is what we get. So, then coefficient of drag, now that is that comes from that is basically how we call CD, right. I mean, how do we define CD? So, this basically comes from the formula. So, if you do that, this is basically drag, over the length L, you could say x, okay. It's basically half rho u square, this is the dynamic pressure, okay, into the area. So, this is a standard relationship, in the sense that when in cases of wings, coefficient of lift, coefficient of drag. So, this is how we define it. So, this is the total drag by dynamic pressure into the area. Okay. So, if I do that in this particular case, what I get is 1.328 by RE, whatever your length, okay, and that is equal to, if you see, 2 times, okay, that is basically, if you see, 2 times coefficient of friction, because as if you see, I wrote this the first time itself, this, right, I wrote this. So, when I calculated this and finally I come to this, I saw CD to be this. This is equal to nothing but 2 times CFL, right. So, CFL. So, if I so you can sort of expand that a little bit. Okay. So, you do this. Okay. Now, okay. So, did I just say that theta by x is point? Okay. So, I haven't given you an expression for theta, or did I? Let's go back. No, I don't think I have. So, let's go back. So, let's go see if we can find something regarding that. Now, momentum thickness, right. Now, this CD thing, right. Now, CD thing, we can write this as 2 theta, of course, that depends on L as well. So, by L, right. So, did we say something about theta by x somewhere? I don't think we did. Okay. So, okay, we didn't say anything about theta by x. Okay, fine. So, so basically this is what we get. So, now this CD, right, CD is equal to 2 into theta by L, right. So, then, so therefore, if I do that, now if I equate all of this. So, therefore, what I get is theta by x is nothing but 0.664 by RE x. How? Because if you see, it's theta by L is nothing but CFL, right. What is CFL? CFL is nothing but 0.664 by REX. So, 0.664 by REX. So, this L, so I have just replaced that by x. So, this is nothing but theta x. So, this is my expression for the displacement. So, this is my expression for the displacement, the momentum thickness actually, right. Now, if I do that, okay, if I do that, then how do I go about this problem? Okay, how do I go about this problem? Well, let us sort of now, before I delve into all these things, now the relationships that we have drawn here, that I've just derived or talked about here, they are for laminar boundary layers, and this is very important to understand. These are for laminar boundary layers. Okay, there are turbulent boundary layers as well, and then we have to take different slightly different things under consideration. So, then the formula will be slightly different. Okay, that is very important. So, the first thing, one thing that when you're going to do the problem that we just discussed. Okay, what I will do here, before I close this module, is that I will just give you some hints. You go ahead and do it yourself, and we will discuss this only in the next module. Okay, this is like a little homework for you. Okay, so what the first things is that you do. So let's do this. This is your to-do list. Okay, so the first things you do, okay, is check. Okay, now check the Reynolds number. Now, the Reynolds number is what? Is rho V d by mu, or this is V d by nu. Okay? This is what it is. Okay? Now, and then I will give you these these metrics. So, if RE is less than 2500, then we have a thick boundary layer. Okay, and delta by x is usually delta by x is around 0.1. Okay, so RE is less than or equal to 10 to the power 3 million, then it is laminar boundary layer, and if RE is greater than 3 million and less than 5 million, then it is turbulent boundary layer, right. Now, these are the checks. Now, what you need to do is go ahead and first check the RE, and make sure that you can actually use these formula that we've just discussed. Okay. So, once you do that, so what you can see here is that when we did this, okay, so look into the formula here. So, this is your CD, right, and we use this, which is we related the Reynolds number. Okay. So, here if you find out the Reynolds number corresponding to the length L, right, you should be able to find out the CD, right. If you find out the CD, then you can find out the drag. How? Because the CD is connected, CD you get directly from the drag. So, then you can find out the drag, right. So, and then if you find out the drag, then you need to find out the delta, delta star and delta theta. So, you need to find out the drag, so you should be able to find out from there. Right. So, then again we have this expression for delta. So, hopefully you can find that out. Okay, this is the boundary layer thickness, and then you have this, which is the displacement thickness. Okay. Laminar flat plate, okay, and there is okay, you get that. So, okay, I will sort of leave you there, and you could also find out then theta. You could find out theta from here as well, and there is something called a shape factor. We will get to that later on, and you basically have two cases to deal with here. So, get some practice. So, you have got two cases, one is for air and one is for water. So, it will be very interesting to see that for the same plate, right, for the same plate, L is 1 meters and B is 3 meters, and the same velocity of 2 meters per second. If the fluid is air, then what is the drag, delta, delta star and theta, instead of if it is water, which is almost 1000 times heavier, right, 1000 kg per meter cube, then how does the drag, delta, delta star and theta change, right. So, this is a very interesting problem. So, it should sort of engage you for a little bit. So, I suggest that you go ahead and try to look into this problem by yourself, and we will come back and look at this in the next module. Okay. So, that should close it. Thanks.